Today, today's lesson is about combinations. What we talked about last week was permutations. I'm going to give you a shortcut way of remembering the difference and an example of how they can be different, and then we'll work some problems. So so here's your shortcut way. Permutations are where you're rearranging things from a group and the order matters. Combinations, which we're talking about today, are where order does not matter. That says does, believe it or not. So here's an example to illustrate. Let's say you have a group of people. You have a group of 5 people. The permutation would be where I say, look, you need 5, you need to assign those people to different positions, like a president, a vice president, a secretary, a treasurer, and something else, okay? You'd have like a president, vice president, secretary, treasurer, and then I need one more. We'll call the last person an assistant treasurer. There is no such thing that I'm aware of. But anyway, so they have to all be placed in one of those positions of leadership, right? Well, you've got 5 people to choose from for the first position, but once someone goes there, they're no longer available for the other spots. And so it would be only 4 options for the next one, and then 3, and then 2, and then 1, right? This is a permutation, and we talked about that last week. A combination would be, though, how many different ways can you rearrange those 5 people where the order doesn't matter? Here, the order matters because once you make one choice, it affects the rest of them. But if you're just simply rearranging them, how many different ways can you rearrange 5 people? And there's no real order to it. Well, now that's a combination. Just how many combinations can you make? So one order matters and one order does not matter. And then this is the mathy definition for combination. It's the number of ways our objects can be selected from a set containing n unique elements when order is irrelevant. Okay, and then this is the formula that we're going to be using. And again, N stands for the number of elements in the set. R stands for how many you're picking out of that set to rearrange. And C obviously stands for combination. And don't forget the exclamation marks stand for factorial. That's when you multiply, if it was 5 factorial, you're going to multiply 5 times 4 times 3 times 2 times 1. Okay. So these first set of examples are just to practice that formula. They're not attached to any kind of actual example or story. We're just going to practice the plugging in. 10C4, your N is 10, R is 4, and plugging it into that formula gives me 10 factorial over 4 factorial times 10 minus 4 factorial. Okay, that's 10 factorial over 4 factorial, 6 factorial. Do not multiply 4 and 6 and make this 24 factorial. Factorial does not work like that, okay? But what I will do is break down 10 factorial till I get to the 6. Here's my 4 factorial. 6 factorial I'm going to leave without breaking it down because I know I can just cancel it out with the one up top. And now you can multiply across the top and bottom. That gives you 5,040 on top, and then multiply across the bottom. That gives you 24. Dividing those things gives you 210. So if you had 10 items and you were choosing 4 and rearranging them, how many groups could you make? Groups of 4. There's 210 ways that you could do that. One thing I like to do, so now going back to this step, if you don't want to multiply across the top and across the bottom, you can also simplify at this step. You could do something like this. You could say 9 divided by 3 is 3. 8 divided by 2 is 4. You could even, the 10/4 right here, you could simplify to 5 halves. And then you could even go one more step. The 4 here and the 2 here simplifies to 2. And now you multiply the 5 times 3 times 2 times 7. And that gives you 210. If you want to simplify in the middle, you can, or just following my blue work, that's just multiplying across the top, multiplying across the bottom, and getting 210. Pause your video and try these next 2 examples on your own and see what you come up with. All right, for the second example, so I erased my previous work to make some room. You should have had 7 factorial. I'm just going to have this video getting my pen right. Okay. 7 factorial over 5 factorial times 2 factorial, because I did this in my head, right? 7 minus 5 is 2. When you break down, I'm going to break down the 7 factorial just till I get to the 5, because I know I can cancel it with the 5 factorial on the bottom. Okay, multiplying across the top gives me 42. Across the bottom is 2, and then that's just 21. So hopefully you got 21 for that second example. And then for the last example, you should have 6 factorial over 3 factorial times 3 factorial. Resist the urge to say everything cancels out because 3 plus 3 on the bottom is 6. Okay, it doesn't work like that. You also cannot do 3 times 3 and make it 9 factorial. Okay, they are separate entities. When I start to break down 6 factorial, I'm going to stop once I get to 3, because I know it can cancel out with one of the 3 factorials on the bottom. Now, multiplying across the top gives you 120. Across the bottom is 6, and that simplifies to 20. So now we'll use that formula to do some example problems. Okay. Pause your video and read example 1 before I read it to you. So we have this chef, Pierre, who is an award-winning chef and has just developed 12 delectable, new main course recipes for his restaurant. In how many ways can he select 3 of the recipes to be entered into an international culinary competition? So the reason why this is a combination is because the order doesn't matter. This would be a permutation if it said 3 recipes, 1 needs to be the entree, 1 needs to be the main course, and 1 needs to be the dessert. That would be ordering it. But this is simply just saying how many different groups of 3 can he choose, and the order doesn't matter. So that's why this is a combination. So we've got 12 possible things, but he's going to choose 3. So this is 12 choose 3, and then we just plug it into our formula. I will break down 12 factorial just till I get to 9. Because I'm going to cancel with the 9 factorial, and then I need to break down that 3 factorial to see what it equals. So those 9s are gone. Multiplying across the top gives me 1,320, and across the bottom gives me 6. There are 220 ways that out of 12 dishes, he can pick 3 to be sent off. I want you to pause your video and try example 2 on your own. All right, the Mu Alpha Theta Math Honor Society. By the way, I was in the Math Honor Society when I was in college. Has 21 seniors. And how many ways can a committee of 4 senior members be formed? So this is out of 21 possible, we're going to choose 4. So we just plug those into the formula. And I will break down 21 just till I get to the 17. Because I'm going to cancel that with the 17 factorial in the denominator. And then the 4 factorial I will break down. So these cancel. And you can multiply across the top and across the bottom here, but I'm also going to show you the way if you want to start simplifying here to make your numbers smaller. For example, 20 over 4 is 5. 18 over 3 is 6. So now up top I'm multiplying 21 times 5 times 19 times 6, which is 11,970. And then on the bottom I have 2 times 1, which is 2. So there's 5,985 ways. All right, last problem. Kate is going to adopt 3 kittens from a litter of 11. How many ways can she choose a group of 3? So pause the video and do that for yourself. So it's 11 choose 3. We're going to plug that in here. I'll break down 11 factorial just till I get to the 8. Because I'm going to cancel it out with the 8 that's on the bottom. And then break down 3 factorial. Multiplying across the top gives you 990, and across the bottom is 6. That means there are 165 ways she can choose a group of 3 kittens. All right, that's it. That's a short video for today.